last time we were looking at permutations and combinations, and we also had the fundamental principle of counting thrown in there. There's two types of permutations. There's really 4 different strategies that we were considering when we were looking at a question asking us to count number of ways things can happen. And I think we're at number 7 example. Is that right? Yeah. Okay. So we don't have a lot left to do. But let me remind you about the basic differences real quick so that we can actually make decisions that seem reasonable when we get to the problems. So let me flip back. The first one was the fundamental principle of counting. And the fundamental principle of counting talks about what happens when we have different sequentially ordered objects or sequentially ordered activities or whatever. And so we end up multiplying their individual numbers together and we get a grand total. So we had this example where we had meals at Pizza Planet. Permutation has 2 types. There's permutation of like objects. The example we talked about was Starburst, but we talked about anything that has like objects. So if you were wanting to know where categories, where it doesn't discernibly make things discernibly different. So an example I gave was to think about if we wanted to have a committee and we wanted a certain number of men and women, or a certain number of freshmen, sophomores, or juniors, or seniors. While those are individually different people, the category puts them into the same thing. So it makes them like objects. Everybody in this category is a female, or everybody in this category is a sophomore. And so we can get things that are non-discernible from that kind of a perspective. So it's not always about candy, although the candy problems are fun. Then we had unlike objects. So in those same scenarios, if we specifically looked at flat out the number of ways of making one of these groups of people, not just whether they were male or female. Those are individually different objects then, and so we would count them as such. And so we have this formula that showed up when we have individually different objects. Now, combinations and permutations are both individually different objects, but in those cases, one of them, permutations, the order matters, and in the other one, combinations, the order doesn't. So one of the ways to you might jot this down as an idea, as to try to distinguish between the two, because sometimes those are the difficult ones to distinguish. I know I've got unlike objects, but which one of these two is it? I can't tell if the order matters. So there's 2 different really classic cases of this. If we were creating something where the order matters, you can think of our raffle examples, right, where everybody gets the same prize, everybody gets different prizes as objects. You can also think of things like when you're creating a group of people. So if you're creating a group of people where the first person who wins gets to be president, and the second place person gets to be vice president, and the third place person gets to be treasurer, something like that. Or not even necessarily first, second, third, but the way that the voting's happening, those offices are doing different things, which they would be. That would make things where the order mattered. If you were simply creating a committee where everybody's responsibilities were shared responsibilities, nobody has different job descriptions, that's a combination, because the order doesn't matter when we're just talking about a committee. So we're going to do a couple of examples. The first one we're going to look at is a worship team. And we also talked about the fact that sometimes you have more than one way of doing a problem that will work. This is actually an example of one of those. So a worship team practices 8 songs on Wednesday night for the Sunday service. If the worship minister plans to choose only 5 of the 8 songs, in how many ways could the songs occur? So, which type of a problem or which strategy do you see that we could use on this problem? You got 4 options, and at least 2 of them work, actually. So you got a pretty good, stab in the dark kind of chance here. You can use the fundamental theorem. Yeah, you can. And that's probably the most direct way of thinking about it. Like if you think about the worship minister sitting there, he chooses out one song, and he had 8 to choose from, right? Now he chooses the next song, and he has 7 to choose from. And he does this 5 times, so all the way down to 4 songs remaining. So we have 5 different songs that are being sung in worship. 8 times 7 times 6 times 5 times 4. And somebody's going to grab a calculator and tell us what that is. I'm just sure of it.
960.
Is it 960? Okay. So there's 960 different ways. There's another way to do this problem, another way to think about it. I think 960 sounds too small, and I'm getting funny faces now. So, Hannah, what'd you get?
6,700.
Okay. It sounded small. I was just trusting you, though. Okay, 6,720. Does that make everybody happier? Awesome. Okay, there is another way of doing the particular problem. So you can definitely, the individual songs are uniquely different items, right? So permutation of like objects is not a possibility. These songs are not like objects. However, I do have the option then of having a permutation of unlike objects or a combination, because those are also unlike objects. So if you're trying to decide between permutation and combination, the question then has to do with if the order matters. So there's a couple of ways that you can know for sure in this context that the order matters. One of them is that we're wanting to know how many ways. Well, if I sing song, Amazing Grace, and then I sing the song, the B-I-B-L-E, that is a different way than singing the B-I-B-L-E and then Amazing Grace, right? So those are distinguishably different ways. So the order matters. The other thing that you can think about in terms of the context of this particular problem is think about from the perspective of the person, whoever does your worship at your church. Do you think that there is a order and a strategy of how they place their songs? Absolutely. So they start with something that's probably like a call to worship, where it's maybe something that's a little bit new or you haven't learned it yet, right? That's usually how it works. And then we move into sort of the upbeat songs, right? And then as you get further into the service, you're getting the songs that are slowing down because you're preparing for prayer or you're preparing to listen to the sermon, depending on what comes next in your order of service. There's an order to your services. Now, my husband, he is pastor and he does our music, and he likes to change up the order all the time. Not at random, but with a specific reason. He's still doing it in an order that he has designed and he has thought through. So that's another way you can know that it's not a combination. The order does matter. So if you think about it from that perspective, this is a permutation. We are having 8 objects and we're choosing 5 of them. And from the perspective of that formula, remember the first number, the larger number, goes on top. And then on bottom, it's the subtraction of the 2. You don't have to write out 8 minus 5. You could just write out 3. But it is the subtraction of the 2. So we end up getting 8. Wow, that's a good 8. 8 times 7 times 6 times 5. And because this is a 3, I'm going to write this out till I get to 3 factorial times 4 times 3 factorial. And then my 3 factorial on the bottom will match up exactly with the 3 factorial on the top. They cancel, and then I'm left with multiplying the same numbers I did when I did the fundamental principle of counting. So I get the same thing either way. The perspective is a little bit different. Okay. Our next example has a few parts to it. Have I explained a card deck in this class? Have I done that before? Okay, Emily, yes.
With the test, will you specify, use this formula if there's, multiple ways?
You can pick it either way. Yeah, so if, I gave you this problem and you thought of it as fundamental principle of counting and Caleb thought of it as a permutation of unlike objects, you're going to get the same answer. Your work's going to be a little bit different, but you're going to do the same. Yeah, it's all good. Yeah. Because what I want to know is that I want to know that you can pick out which formula of the 4 to use, period. And if 2 of them equally work, well, then that's fine. Okay, so I have talked about standard deck of cards, right? Reds and blacks and kings and queens and all that stuff. I thought I had. So we're going to use our standard 52 deck of cards, and we're going to deal out a card hand of 5 cards. So as we think about this, we have to think about if the order matters. I've definitely got 52 objects, and I'm choosing 5 of them. So this is a permutation or a combination type problem. I've got a bunch of things, and I'm going to select a smaller number, okay? But the question is whether or not the order matters. So when you're doing a game, and I don't even care if it's what game, it really makes very little difference. You can be playing gin rummy, you can be playing Uno or Skip-Bo or 5-card poker. I don't care. It doesn't matter. Does the order in which the dealer gives you your cards have any bearing on your game? No. Once they're in their hand, in fact, what you probably do is you probably rearrange them into a way that makes sense for that game, right? So the order does not matter. So since the order does not matter, what does that mean that we're going to use? Combination. Which is actually a little interesting because when you think about the combination lock, y'all know what I'm talking about? Do you know what a combination lock is? Order matters in a combination lock. It really should be called a permutation lock, just so you know. To confuse the issue, right, within English and math. So this is a combination. We are selecting 5 cards from 52. So 52, choose 5. Now the combination formula has the 52 factorial on top, and then it has that same 52 minus 5 factorial on bottom, but it also has a 5 factorial on bottom. We haven't done as many combination problems. We've only done one, and we did it 2 days ago. But what you should remember anytime you're working with permutations or combinations is that you're going to get a whole number out of this. And the only way you're going to get a whole number is going to be if everything in the denominator cancels. So we're going to work towards canceling out the entire denominator to make it a little bit easier to work with. So 52 minus 5 is 47. So I'm going to write my digits out, 52 down to 47. So 52, 51, 50, 49, 48, and 47 factorial. This is a very good example of one that, even though there's a factorial button in your calculator, you cannot find 52 factorial exactly in your calculator. It's too big. So we definitely want to write things out and condense and reduce them sooner rather than later. And then my 5 factorial is 5, 4, 3, 2, and 1. So at that point, those 47 factorials being exactly the same will cancel out completely. You can pair things together. You can do them one by one. It doesn't make any difference. Maybe you very quickly see, hey, there's a 5 and a 50. You probably see that one, right? It's going to be a 10. 50 divided by 5 is 10. What's another one that you see that divides nicely? 2 and 52. So 52 divided by 2 is 26. Okay, we need to do the 4 and the 3 still. 51 and 3 will divide. 51 divides by 3 because 5 plus 1 is 6, and 6 divides by 3. A little bit of number theory. What is 51 divided by 3? It is 17. Okay, so now I've got a 26, a 17, and a 10. How about my 4? 4 and 48 works nicely. So 48 divided by 4 is 12. So be very careful in collecting all the things that are remaining, that you don't miss one. It would be easy on this one to miss the 49 because I did never adjust anything with it. So we need 26 times 17 times 10 times 49 times 12. How many different 5-card hands are there? What'd you guys get? 2,598,960. That's a lot. And it really is. And that's why it starts to become very obvious why playing cards is such a randomized event that you can play the same game so many times and it doesn't lose its appeal, right? It doesn't become the same thing over and over again. All right, so we're going to change the rules just a little bit with Part B. Instead, we want to know how many all diamond hands we could have gotten, okay? So we don't want to select all cards. We really want all the cards that ended up my hands to be diamonds. So instead of having 52 any cards, how many diamond cards are there? 13. So there are 13 different diamond cards. Still a combination, still can shuffle up my hand, right? And I want to select 5 of them. Okay? So I have my 13 factorial on top. I have 13 minus 5 factorial on bottom, and then another 5 factorial. What is 13 minus 5? It's 8. So I'm going to write the 13 factorial down to 8. 13, 12, 11, 10, 9, 8 factorial. That will match with what's on the bottom. And then 5, 4, 3, 2, and 1. So those 8 factorials, gone. We'll pair them up this time just because we haven't done that. I can do the 5 and the 2 paired up nicely. 5 times 2 is 10, which cancels very nicely with something on top. You can do it piecewise like we did last time if you prefer. This one works nicely. The 4 times 3 is 12, and that cancels with my 12 on top very nicely. Be sure and collect all the pieces that didn't cancel, which are my 13 times 11 times 9. So what is 13 times 11 times 9? 1,287 hands. Now, when you play certain card games like this, where you have the 5 card games and so forth, that's not very many, right? 1,287 compared to 2,598,960 hands is not very many. So it's not very likely that you're going to get a hand that's all diamonds. So what that means when people gamble is that if you do get that, it's a really rare thing, right? So it becomes sort of an attainable goal among other types of disbursements of cards. So what we're doing on part C is we're actually finding the probability of getting all 5 diamonds. So we're combining what we've been doing in this section with what we did in the previous sections on probability at this point. So what is the probability of getting all diamonds? Well, it should be the number of ways of getting all diamonds, which we did in part B, divided by the number of ways of getting anything, which we did in part A. Does that make sense? There's 1,287 hands of cards that match this criteria, right? And there's 2,598,960 different options that we could have pulled. So as we do this, I don't want to leave this as a fraction. This would be ugly. So we are probably going to have to round, and that's okay. So the basic rule of thumb as we're working here in this section on rounding when things are not exact is we're going to round to 4 decimal places. Okay, that's our basic rule of thumb. So if you want to jot yourself down a note, we're rounding to 4 decimal places. So if you grab a calculator and you do this division rounded to 4 decimal places, what do you get? 0.0005. If you wanted to think about that in terms of like percentage chances, if you multiplied it by 100, so this isn't part of this answer, but just to give you some perspective, this is 0.05%. That's really, really small, right? Kind of like a, it's never going to happen kind of number, right? It's extremely, extremely rare to get a hand where all 5 cards are of the same suit. So funny story, my dad used to be a card player when he was living, and one of the games he really liked to play was Rook. I don't know if you've played Rook before. It's like spades, but with specific types of cards. And one time we were playing, and he decided that he was going to trick me. And I had left the room to get a snack or go to the restroom or whatever, and I come back, and I had a whole hand of all the same suit. I don't remember what it was. It was probably actually I think it was yellow, to be honest. I mean, there's colored cards there. They were all the same. So he wanted to see how I would react, right? There's a bidding process in that game and so forth, how I would react, because like that's never going to happen, right? It's never going to happen. All right, we're going to do a committee example. I've alluded to this problem with freshmen, sophomore, junior, seniors a couple of different times. We're creating a committee of people, and our committee of people, while they are, of course, distinctly different people, all we care about is their classification. So because that's the case, they are not actually discernibly different, right? They're not discernibly different. In some fashion, you could think about it almost like it's a permutation of like objects because they're not discernibly different. But you can also think about the fact then that the order of them doesn't matter. All right, and that's actually the easier way to think about it in terms of the rest of the problem. So it says we want a committee of 3 people. We're selecting from seniors, 7 seniors, 5 juniors, and 3 sophomores. We want to know the probability the committee consists of all seniors. Now, hidden within this question is actually both of the questions from the previous problem, Part A and Part B. Part A, which would actually say, well, how many different committees are there? And Part B that says, well, how many committees are there for Part A? And then Part B that says, well, how many committees are there that actually meet your criteria? And then I can put things together like I did in Part C and find a probability. So this question is really 3 questions in one. We broke it apart last problem. Here it's all combined into one question. So what I need to do is I need to find the number of committees total. And I need to find the number of committees that are, I think it said all seniors, right? So all seniors. And then I'm going to need to find the probability of all seniors by dividing the number of all seniors by the number of committees. Do you understand the basic 3 things we need to find? Okay, fabulous. So because these are not discernibly different positions, like we talked about earlier, the order doesn't matter, right? If I selected a committee, it doesn't matter if you're selected first or you're selected third, you made it, okay? So my committee needs to be from among all the people that I have to choose from. So how many people are there? There are 15 people. And how many am I choosing? 3, because my committee said it was 3 people. And why am I, where did we get the 15? Yeah, we just added all our people together, right? Okay, and that's what I was going to say about the committee, the C. Why is it a C? It's a combination because the order didn't matter, right? So that's why I'm using C instead of P. So I have 15 factorial on top, and then I have 15 minus 3 factorial on bottom, and 3 factorial on bottom. What is 15 minus 3? 12. So I'm going to write my 15 out till I get to 12. So I have 15 times 14 times 13 times 12 factorial. There's that 12 factorial on bottom. Then I have 3 times 2 times 1. So the 12 factorials cancel completely. How about my 3 and my 2? 3 will go into 15 5 times, and 2 will go into 14 7 times. So we're going to multiply out 5 times 7 times 13. So what is 5 times 7 times 13? Yes. Sorry, I was looking at the wrong place on my notes. I was like, what does that mean? Yep, 455. Okay, so that's the way of getting any people on the committee. Now I want to get just seniors, okay? I want to figure out how many ways I can have a seniors-only committee. So how many seniors are there? 7 seniors. And again, the order that I choose them in doesn't make any difference. You're either chosen or you're not. So I have 7 factorial. I need to space this down just a little bit. 7 factorial over 7 minus 3 factorial. 3 factorial. So 7 minus 3 is 4. So I'm going to write my 7 factorial out. If it happens, and it could happen, I should probably make mention of this. It keeps happening so far that the first number ends up being the one that I'm writing out till. You're just writing to whichever one's the bigger one. It just happens that 4 in this case is bigger than 3. So if I had done 7 choose 5, and I did 7 minus 5 here, and it was a 2, and this was a 5, I'd write it out to the 5 factorial. So I'm wanting to use the biggest number I can cancel. So 7, 6, 5, and 4 factorial with another 4 factorial. And then 3, 2, and 1. So 4 factorials cancel. And then what? 3 times 2 is 6. So I'm left with 7 times 5, which is 35. So there are only 35 different committees that could be compiled of just seniors. And then if I'm trying to find the probability, sort of part C, if you will, of this particular portion of the problem, then I want to have my 35 group, number of ways of getting committees of all seniors, divided by my total number of committees, which is 455. And again, we'll do this to accurate to 4 decimal places, and we'll round it off. What is 35 divided by 455? So this is a bigger number than last time, a significantly bigger number, actually. So this is about 7, almost 8%, right? Because if I multiplied this by 100, I would be getting almost 8%. So that's not nothing, but it's still pretty small. I mean, and if you saw something that had an 8% chance of it happening, you probably wouldn't be too worried, right? If somebody told you there's an 8% chance of thunderstorms tonight, you'd be like, okay. I mean, right? You would. So it's not a huge number. The other problem then says, what is the probability it has no seniors? Now, part of the work is already done. The part that's already done is this total committee's work. Everything we did right here, we need on the next page. We don't need to recreate it. So don't go doing the work twice. That's just silliness. We know that the number of total committees is 455. I don't need to do that again. But what I do need to do is I need to find the number of non-senior committees. And one of the things you might be tempted to do, because we've seen this happen before, is say, hey, look, if there's 455 committees that are total, and there's 35 that are all seniors, I could subtract those two. The problem is that some of those still committees that you would get in that subtraction would still include some seniors, just not all seniors. So that's not quite the question, right? The question really wants only sophomores and juniors on the committee. So we're actually going to replicate this process right here almost exactly, but with the sophomores and juniors being counted instead. So how many sophomores plus juniors do we have? We have 8. So on this one, we have 8, and we're choosing 5. So I have 8 factorial over 8 minus 5 factorial, 5 factorial.
Why is it 5 to get 5?
Because I wrote it down wrong. Thank you. How about we do 3? That'd be better?
Yes.
Awesome. Thank you for catching it. I would have gotten to the end and been like, oh no, my notes don't match. Okay, yeah, that's better. I do get a 5 here, so maybe that's what I was already moving towards. We'll pretend that for the moment. All right, so we're going to write our 8 out until we get to 5. 8, 7, 6, 5 factorial with 5 factorial, and then 3, 2, and 1. Just like last time, my 5 factorials cancel. And actually on this one, just like last time, I have a 6 on top, so 3 times 2 is 6. What is 8 times 7? 56. So the part C, if you will, here, where I'm finding the probability of no seniors, I would have my 56 out of my 455. And this should be slightly bigger, right? Because the previous one was 35 out of 455. This one's 56 out of 455. What is my probability on this one?
0.1230.
I think it's 3-1. Is it 1? Okay. So I've got about 12%, right? If I move the decimal 2, I get a percentage. This is about 12%. It's definitely more likely than the other one. Still not anything to sort of, like hang our hat on happening. It's not probably going to happen. But it's more likely than getting all seniors. But that should make sense, right? Because there were fewer seniors than there were of the other classmen. So that's a reasonable thing to have happen. Any questions on that? All right.